In the earlier class, we discussed about Aristotle's fallacy. Okay, what is Aristotle's fallacy? To maintain a uniform motion, you need a force. Okay, continuous force. Then only uniform motion can be achieved. Okay, which was later modified by Galileo, and then which was Galileo. Galileo was to suppose if you don't have any resistive force or anything is there, so which was later used by Newton to derive the laws of motion. Okay. Now, so what is the laws of, okay, you read about the Newton's law of motions in your earlier classes. Okay. So anyway, this time we will see it in a more proper way. We will study about the Newton's law of motion in its exact form. Okay. So what is the first law? Every inanimate object, inanimate means non-living being, okay, non-living object. Every inanimate object continues to be in a state of rest or in uniform motion, uniform unaccelerated motion. Okay, uniform motion. That uniform motion means actually not accelerated. Okay, unless and until it is acted upon by an external force, which is external unbalanced force. That's important. So what it says is a body remains to be in a state of rest. Okay, if I hold the pen like this, the pen is going to be in the state of rest unless and until there is an unbalanced force going to act on it. Okay, suppose if the body, suppose I am holding the pen is at rest, but is there no force acting on it?
There is force.
Yes, one is a gravitational force acting on it, and my hand is giving an upward thrust. So both the forces are equal in magnitude, so they cancel each other and the pen is at rest. Suppose if I lift it, that means the upward thrust I am going to increase it, right? So it is unbalanced force. Or if I am dropping it, it's a unbalanced force. Okay, so what it says is every body remains to be in a state of rest. The similar thing is a uniform motion. You roll a ball in space or whatever it is, okay, it remains moving. They don't stop, okay, unless until you put an external force to stop it. Okay. So, and this is what Newton's first law of motion. Okay. And okay, I will come to about importance of this law later. I will come. Okay, we can speak about the importance of this motion, importance of this first law. What is that? What we wrote? Newton's first law. Or I will just write first law. First law. The first law is also called as the inertial law. Okay. What do you mean by inertia? Inertia means, you know what I mean of the word inertia? You don't want to move. You want to remain the same. So that's why it is something like that. First law says that every body remains to be in the state of rest or in uniform motion unless and until you define. So this law is what is called as the inertial law. And why this law is important is, what is important in the law is, this gives a kind of an equivalence between two states, state of rest and the state of motion. Okay, why it is equivalence is, okay, how to see it is, suppose for example, you are moving in a bus with a uniform bus which is moving in a uniform velocity, it's a uniform motion. Okay, so for example, let us say there is no friction, nothing is there. So if you push it, if you give a force to give a body to move, that body will keep on moving. Okay, so what you will see, suppose you are co-passenger, suppose that you are in such a bus where there is no force moving in a uniform velocity. What will be your co-passenger? Will he be in rest or in motion?
Rest.
He'll be in rest. Okay, so for you, basically what happened, you both are in rest with respect to you. But for some observer outside, for him, you both are moving. Motion. Okay, so what happened? For him, the observer outside will say, according to Newton's first law of motion, you both are continuing with a velocity. You will remain moving forever unless and until you put a stop of external force to it. Okay, and similarly, when you are inside the bus, when you see the co-passenger, you say the co-passenger is going to remain rest always. Okay, unless until an external force is acted upon it. So what it says is, so it is all reference, which with reference to which you are speaking about. You got it? So for in your reference, the person who is sitting in the bus is at rest. For the person sitting outside, the person sitting is not at rest. So he is in a uniform motion. For you, it's at rest. Okay, so this is what the equivalent. So the rest and something which is at rest or something which is in motion, it whole depends upon which respect with reference, which reference you are going to speak about it. So what in physics what they call is a reference system. What do you mean by reference system? Reference system is nothing but a coordinate system. Every one of us have our own coordinate system where we sit in the origin. And with respect to our coordinate system, we try to see what are other motions. Okay, so that is what you call as your frame of reference, my frame of reference. That means what I am in what I do is I put myself in a coordinate system. Okay, and I sit here. Okay, let me put up here. Okay, according to me, there's another one person. Okay, so there will be another one person sitting here. He may be stationary. Okay, so he's at rest. Now, but actually there is a third person reference system. So in his reference system, this reference system is also at rest. Okay, this is your X, what you call Y and Z. Am I right? X, Y and Z. So there can be another person. Okay, for you both are at rest. For another person, another reference system, the person is standing here. For him, you may be moving. Okay, for him, both of you may be moving at a constant velocity v. Okay, so let us speak about the person in blue frame. So the blue frame is in rest for you. But the same blue frame, is it rest for this frame? No. Okay, so it's the equivalence. It doesn't matter. Means it's all. Basically, it's a state. Which state it is? Either a state of the Newton's first law try to unify this. Your motion or rest. This all actually is a very it's a bit reference system you are going to speak about it. That's what I say. It shows the equivalence between the state of rest and the state of uniform motion along a straight line. Yeah, that's important. It has to be a straight line. Do you know why?
Linear motion.
Yes. Why it is linear motion? It has to be a straight line because for any curved motion, you remember circular motion or a parabolic motion, what you need is an acceleration. Okay. Got it? So acceleration. So what it says is, if there is acceleration, the external force is acting on it. Okay. So our point is there is no force acting on it. That means there is no acceleration. If there is no acceleration, the motion will be always on linear. Okay. So good. So what it says is, so this shows the equivalence between the state of rest and the state of uniform motion along a straight line, as both need a net unbalanced force to change its state. So suppose, for example, for you this is at rest. If you want to change its state, what is its states according to you? That's at rest, state of rest. If you want to give an uniform motion, then you have to apply a force. Some force has to be act on it. It starts moving. Okay, and similarly for this person, this is an uniform motion. He will say, when I can change the state of rest, you have to apply a force so that it becomes at rest. Okay, so that's what it says. Okay, both need a net unbalanced force to change the state. Okay, and both these are referred as state of motion. Remember, so therefore, your state of rest, what we write? Inertial law. Inertial law has two things. That is state of rest and state of motion. State of motion. Am I right? What I said? State of motion. Yeah. State of uniform motion. What we have to mention, that is better. Yeah, uniform motion. Na? So what it says is both are basically equivalents. And you can call that a state of motion. Because a rest in one frame doesn't mean rest in all other frames. And a constant velocity in one frame not necessarily mean a constant velocity in all other frames. Okay, so this is what is state of motion. So that's what your bodies at rest as well as bodies in motion, they both are important. Okay. And this is the one. Yeah. So, and this, okay. This distinction between the state of rest and uniform motion lies in the choice of the frame of reference. This is what we call as a frame of reference. Okay. Where you are associating your reference system. Frame of reference is the coordinate system which are attributing to measure different happenings. Okay. So, that coordinate system can be differ for different observers. If I am an observer, I am going to choose a coordinate system according to me. Maybe I will choose my coordinate system as where I sit in the origin and choose it. Suppose for a different observer, he will use different coordinate system. So that's what we call the frame of reference. So the coordinate system which I am going to use is my frame of reference. Okay, so there are cases many times you say, so if there's a car is moving at a constant velocity, you can have a reference frame associated with a car. So in the car's frame of reference, everyone sitting in the car are at rest. Okay, but for the observer, okay, or the observer, otherwise called the lab frame, means where I am sitting outside the experiment. The lab frame, it is not at rest, they all are motion. Okay, so this is what is a frame of reference. And the second thing is, this was an important one. It defines force as an entity. So, see what happened? So, by this, so now, what it says, so it basically it starts defining a state of motion. Am I right? You have the Newton's first law defined a state of motion. And after defining the state of motion, then also it introduces force. So if you want to change the state of motion, then you need another entity, which you call it as a force, that should be applied so that you can change the state of motion. Okay, so that's the important part of it. So this is, so that is, force is something that initiates a motion or controls a motion. Okay, it initiates a motion. I don't know what they mean by control a motion. Rather, what I would say is, which initiates a motion means, which is, we should not call as control a motion. You can modify the motion. Basically, what the force is something which is going to modify that motion. That word is not correct, controls the motion. So now if you see, so in this whole law, first law, so he has not defined, Newton has not defined what is a force. How can you, suppose certain, given a body of mass m and some velocity is moving, how much force should I apply to stop it? Or if certain body is at rest, how much force should I give to give it a uniform motion? He has not given what should be the value of force. What he says is there is an entity named force which is required to change the state of motion. So this type of law is what you call as your quantitative or qualitative. Qualitative. You are not giving the exact formula to it. Newton's first law is a qualitative. Okay, and why this is important? So this actually defines your state of motion. Because why it's important is it brings both. If you go back to that period, you are trying to see a body which is at rest and the body which is at a constant velocity are one and the same. Okay, so that concept is very different. Today now we know it. When you go belong to the Newton's period, someone is telling a body is moving at a constant velocity and a body is at rest. They both are the equivalents to each other. So everyone will laugh at him. Okay. So since it is Newton, nobody laughed at him. Okay. So that's why it is important. That's why this law is. This law gives you the equivalence between the rest and the uniform motion. And not only that, it gives to change the state of motion, you need something entity force. So it's a qualitative description of it. Yeah, and this is another, that's why I said it. It defines the inertia as the fundamental property of every physical object. Inertia. This is inertia. Am I right? If I am remaining the rest, inertia means what? I don't like to change. I don't like any something to affect me. I should like to remain. If you are sleeping, you don't like anyone to wake you up. You want to remain forever. Okay, that we'll see always for the rest we can do. Suppose if you are on motion or doing something, you always wanted someone to interrupt you and stop you. Okay. So fine. So this is what? So this is what called the inertial law. Inertia. Inertia is what? Okay. See why? Okay. See what happened here? What I said, inertia is something we don't like to change. Change it. Okay. And what change? What state of motion? Why we are mentioning state of motion? It is not that suppose a body is at rest, it remains to be rest always. If a body is at uniform motion, it remains to be uniform motion. For us, it doesn't matter because a body is at rest or the uniform motion, they both are state of motions. Okay, so what it says if a body is at rest, it has to remain at rest. So the same body, if you see from another frame, may moving with a velocity. And there says, the inertial law says, since the body is at rest, that means from that reference, if it is moving, it tries to remain in the same velocity. Okay, so it doesn't want to stop or accelerate or anything. So this is inertial law. Okay, and actually the inertia is often associated with the mass. Yeah, exactly. They written it. Yes. Yeah, what it says is it's a physical. It's a fundamental property by which every physical object resists any change in its state of motion. That's what I said. Okay. Inertia is measured as the mass of the object. More specifically, it's called the inertial mass. Okay, inertial mass, because this is what this comes with the this has to combine with the second law. Okay, because if you remember earlier what you studied is you must study in earlier class. Force is equal to mass into acceleration. Okay. This is what you studied in the earlier class, but now you should have one arrow here. Am I right? Vectors. These are vectors. What is a vector? So the mass will be equal to. Is that correct? Can you divide a vector? Yes. Take the magnitude of it and divide it. Okay. So that's what your mass. This is what you call the inertial mass. Okay, and yeah, why this inertial mass comes into picture is, well, this is not always true for writing this. Force is not always equal to mass into acceleration. That's what you have studied. But in fact, this is actually not correct, not exact. Only under certain conditions, force equal to mass into acceleration. When happens? When your mass of the body remains constant always. If the mass of the body doesn't changes, then only you can write this expression. So, and that is inertial mass is defined as that. Okay. So, this comes from the second law. So, and that's what we speak about the first law of motion. Now, come to the second law. You understood first law, right? And why it is called as inertial law, that also you know, right? And this is very important. So then, if I define the inertial law, actually, I can take you that, but anyway, in the next class, I will touch that. When I say inertial law, and I said references frames also, right? So then, I can see all these reference frames. Something is moving at a constant velocity, and you are also moving along with it. So for you, that person is at rest. Okay, and then for the person outside, both of you are moving at the same velocity. You have all these reference systems. Okay. These reference systems are connected by the Newton's law because there's no force acting on it. When there's no forcing acting on it, everything moves in a constant velocity or at rest. So this reference frame of references, where either the frames are moving at a constant velocity, okay, and a linear velocity. Velocity means straight line. Okay, so constant velocity. So those reference frames are called as the inertial frames. Okay, why is inertial frames? They all satisfy your first law of motion, inertial law. There's no forces acting on it. They all move in a very linear one. Okay, so that we will see it in the next class. Fine. So now come to the second law, Newton's second law. Second law is interesting. What second law states? Second law states is interesting. The rate of change of linear momentum of a rigid body is directly proportional to the applied force and takes place in the direction of the applied force. So what you have, yesterday we defined, right? What do you mean momentum? P. Momentum is a vector or a scalar? What's momentum formula? P equal to mass into velocity, right? Vector, because V is a vector, so momentum is also a vector. What it says is the rate of change of momentum. The rate of change of momentum, we know how do you define a rate of change of momentum? Momentum by time, that's in your earlier class. With the math, the last chapter, what we did, rate of change of momentum is defined as dp by dt. Am I right? Oh, sorry, dt is not a vector. dp by dt. Okay, so this is what you call as your time is not a vector. Okay, but there are, or even later on class you will understand that. Okay, there are a lot of discussions about whether time can be a vector. These are not okay. These are just advanced discussion. But for every reasons we can call time as a scalar. Okay, so well, so dp by dt. That's what a rate of change of momentum. So what the law says is the rate of change of linear momentum. That means along a straight line. Okay, linear momentum of a rigid body is directly proportional to the applied force. So what it says is this is proportional to the applied force and takes place in the direction of the applied force. Same direction. Okay. And now this is the law. This is very interesting. Why this is interesting is, see the line carefully. The rate of change of a linear momentum. Linear momentum is what? Uniform velocity. Correct? Because linear momentum is a straight line, it is moving, the velocity. So that means it's actually connected to your first law. Okay, the rate of change of a linear momentum. So earlier what we said, a body remains to be in the state of rest or state of motion. Okay, that means let us take the body is remaining in the state of motion. Okay, suppose if I wanted to change its state, I have to apply a force. What do you mean by changing its states? Initially it was in velocity, maybe it must have stopped at rest, or it must have changed its velocity. Changing its velocity means change in your momentum, change in your linear momentum. Okay, the change in your linear momentum, the change in the linear momentum is proportional to the force applied. That's what your second law is. Okay, and now interestingly, so what we write is, so this, okay, so if I want to write it, so then I can, the way you write it, so force should be equal to some constant times dp by dt. Am I right? Proportionality. This is the proportionality constant. Actually, we can neglect this proportionality constant. How? This, we don't need it. How am I going to do is, so this is a force. Force is a quantity. See, remember, just now only I am defining in the whole, when I derived the law of motion, equations of motion we studied. There was no concept like force. All we had initial velocity and acceleration. We never discussed about force. Okay, so this is a time we are defining what do you mean by force. We are defining the state of motion and we are defining something called as force. Correct? So then, so we don't have, so what I can do is, you can rewrite this equation as, suppose if I take this k here, okay, and I together with f by k, I don't know what f is. I will call this as my force and give a unit called as 1 Newton, a Newton or whatever. 1 Newton. Okay, so what happened? I can include this constant. I don't have to really bother about the constant. I can define a unit such that it takes this proportionality constant taken together only, I'll call it as a force. Anyway, it's a constant, right? So in that case, what happened? I don't have to write like this. Then I will say, okay, let me call, then I will call this force, when I modify this force, let me call it as F Newton. F Newton is what? That has already taken the constant. Doesn't matter about the constant. So then I can write your F Newton force is equal to dP by dt. So what we have done is this proportionality constant by choosing the choice of choice of units, we have actually swallowed the proportionality constant and we wrote it. You got it clear? See, that's what they write it here. See, on selecting suitable units, it takes the form F equal to dP by dt. Okay, so I don't need to remind Newton. Just because I know that's what the unit I'm going to use it for. So I take the force equal to dP by dt. My unit is defined with considering that constant. Okay, so that's how you can, using a proper unit, we can actually define the. So in your SI units and all, this comes up. Suppose if you're using a very arbitrary units, that time you may have to probably use the proportionality constant if you have not taken all these other quantities properly. Why? Because you have defined the entire calculations, assuming k equal to 1, because you are defining as a newtons. Someone if it's using a different unit, then you have to identify what should be his k for it. Okay, so that is one of the thing will come up. So now this is very interesting. So now F is equal to, so now I can write F is equal to dP by dt. So you know what the momentum is, right? What is the momentum we had? If you remember what the momentum we wrote yesterday, P is, you know what, P is equal to M into V. Okay. So now you are, therefore, so dF by dt will be equal to, let us substitute. So this is going to be d by dt of mv.
Mass is a constant, so we can take it out.
If mass is not a constant, so then what happened? You remember? D by dx of f1 of x plus f2 of x will be what?
D by dx of f1 x.
Oh, sorry, f1 of x into f2 of x, na?
F2
f1 of x into df2 by dx plus f2 into df1 by dx. Now tell me what this will be.
V into
Want to first write v or m into
d v by dt
plus
v into dm by dt.
correct. So what it says is, so if your mass is changing with time, okay, so I will give an example. In the book they give a very nice example, okay, or sometimes you are what is that, something okay, yeah, many times if you are something you are moving, something is moving in a constant velocity, and if it's shredding off certain things, then the mass is not going to be same. One good example they given is a rocket. As a rocket goes up, the fuels are being burnt, the fuels are being exhausted. So of course, even your cracker, when you put a cracker rocket or something, when you do this cracker which goes up, after some time the fuel is being burnt off, right? The mass is not going to be same as it was ground. The rocket also. And possibly when it goes to one stage, second stage, the whole one portion removes and breaks and goes off, right? So in those cases, what happens? The mass is not going to remain as a constant. The mass is going to change, okay, with time. So then this is not going to go zero. Only the case if the mass is constant, m equal to a constant, then dm by dt for a constant, what we know, that's equal to 0 because it doesn't change. Am I right? So in that case, this equation is going to become, so this becomes 0. F will be equal to m into dv by dt. That's equal to m into a. Got it? So this is under the specialized case when your mass is constant. So whenever you write F equal to ma is not always correct. It's under the assumption mass is constant. Okay? So this is what your second law is. Okay. Yeah, and that's also correct. So yeah, so from here also you can say, so this actually answers your first law also. It comes from, because F equal to 0, dv by dt is equal to 0.
Okay.
Am I right? So that means what? There is no change in the velocity. Okay, there is no force acting. That's what your first law is. Okay, so what is the beauty of the second law is it gives you, see, but first law is what? Qualitative. It have not defined what is the force. It says this is an entity force which changes the state of motion. Second law says,
What the entity of force?
yes, what that force is. If something is changed its state of motion, then what should be the force is? That basically the force will be nothing but the rate of change of the momentum, linear momentum. So this gives you the, which way? Quantitative measurement for force. Okay, so that's why second law is important. Okay, and the importance of second law is what? Yeah, it gives a mathematical formulation for the quantitative measurement of force. You got, that's the one thing. Yeah, that's the very important part. And the second law, the important is, suppose if you see in the first law and second law, okay, we have not defined something called as velocity. Though we know uniform motion means a constant velocity. Okay, so the second law doesn't speak about velocity. It speaks about momentum. So it brings momentum as a fundamental quantity. Okay, because to give a certain velocity, as I told you yesterday, right? A same force cannot give a same velocity for different objects of different mass. Okay, if I throw a stone ball, so if you throw a plastic ball, iron ball, or a cricket ball with the same force, the trajectory is not going to be same because my initial velocity is going to be different because of the momentum. Okay, so this is something, but so it starts giving the momentum as a fundamental quantity, not the velocity. Okay, like in our equation of motions, we always consider the initial velocity as a fundamental quantity. Initial velocity, give me the initial velocity and give me the acceleration, I can tell you what the trajectory of the particle is, what the time and everything. But this law of motion says, no, not the initial velocity. What important is the momentum. Okay, that's what it says. It defines momentum instead of velocity as a fundamental quantity related to motion. Okay, so what is changed by a force is the momentum and not necessarily the velocity. Okay, of course, velocity also changes. But what important quantity changing is the momentum. The change in momentum which is eventually giving rise to a change in velocity. Okay, and yeah, and the other important thing is, okay, yeah, this is, okay, they written here, Aristotle fallacy is overcome by considering the resultant unbalanced force. Okay, that's right. Aristotle fallacy is basically overcome because the force is all acting. See, any unbalanced force, of course, your ball needs a continuous force to have a uniform motion because there's unbalanced force acting on it. Okay, that's a resistive frictional force, whatever. Okay, so that's what Aristotle fallacy is also overcome by this, the second law. Now let us come to the third law. And third law is, okay, this first law and second law, more or less, they both are, one is a qualitative description. That's the inertial law. And that qualitative description is important. If you don't have the qualitative, see, your point is when I have a quantitative description, why do I need this qualitative description? Okay, the qualitative description is required to define something called as inertial frames and non-inertial frames, which we will see it in the next. Okay, second law doesn't give you the inertial frame. So this inertia concept comes from the first law. Okay, so that's what. So now let us come to the third law. So what is the third law? Okay, let me write down the second law here. Force F is equal to, anyway, we are not going to write down the proportionality constant hereafter. We will write it as equal to. Okay. So this is your second law. So now let us come to the last law. So that is the third law, Newton's third law. So third law says, you know, third law is very easy. Am I right? What is the law? Tell me. Correct. For every action, there is an equal and opposite reaction. If you slap someone, the person will slap you back. Okay. Am I right? Okay, reaction. So action here, when they mean action and reaction is basically force. Okay, and that is the point. And this is a very special law. Though at that time everyone were knowing it, giving this law is very important. The point is, you put a ball, drop a ball, the ball bounces back. Okay, and this, interestingly, this doesn't bother about uniform motion. So earlier we all having the force and acceleration. First we defined about the state of motion. Second we defined about the force. Third says it doesn't bother about because the moment now I'm going to action and reaction, force and the reactive force. But the moment when now the forces start playing into it. Okay, the motion is not no more is going to be uniform motion or rest. Okay, so what says is, for every force applied, you have applied a force. It says the force is what? dp by dt. You got it? For every force, and there is an equal and opposite force will be applied on you. Okay, so what it says is, if I take a gun, fire a gun, that means the gun has applied a force on the bullet and the bullet is moving. So what is that force? That will be dp by dt of the bullet. Correct? Am I right? dp by dt of the bullet. Now the bullet applies another force on the gun. I'll get the gun on the back jerk. Okay, and that is a reactive force. So that is again dp by dt of the gun. So now both the force has to be equal. Okay, so now the momentum, change in momentum, m, the mass of the bullet is very small. Okay, so entire momentum is in the velocity. Okay, so what happened? We are having two quantum. So let us say momentum of the bullet, p bullet, will be m1 and v1. Momentum of the gun will be m2, v2. Okay, so of course m1 will be very, very small to m2. Now if they both should be equal, am I right? So naturally your v1 has to be much, much higher than your v2. That's why when you shoot, the gun doesn't go with the same speed on the back. Okay, the bullet goes. Of course, the gun is massive, so you can handle it. Okay, that's why the olden days, the rifle, they put it on the shoulder and do it. And if you don't hold it properly, it can create a fracture also. That should be the recoil. So when you fire a bullet, the gun recoils. That's because of Newton's third law of motion. Okay, so there will be equal opposite force. It's anything. You toss a ball, the ball comes back. Okay, and the ball comes back to you. Or you drop a glass bottle. It goes and, okay, what happened? The bottle go and exert a pressure on the floor, force on the floor, and the floor will go under force on the glass bottle will break off. Okay, so this is what your Newton's third law. Okay, so it's very important. Okay, and okay, what the importance is, it defines action and reaction as a pair of equal and opposite force acting along the same line. When you drop the ball, the same way it bounces back. Okay, is that true always?
No.
If I drop at an angle, will it come back at the same angle? No. Okay, but it says the same line. Can you think? Okay, what is the question? So let us say. So there is a floor. You are going to drop a ball, bounce a ball. The ball hits the ground. The ground exerts a force back on the ball. And if it is the same line, you will think it should come back here, right? But the ball goes here. Okay. Why? There is a velocity you are giving. Momentum. It has two components. Okay. This is what? Let us call this as your, tell me, which one angle? You want to Vy, you want to call it? Vy, and this is Vx. Correct? So now what happened? So is there any change in the Vx? Where the force is acting? The force is acted by the ground, right? So only this momentum. Yeah. Only the momentum, the yth component of the momentum, Py, which is equal to Mvy. Okay, this is going to cause a force on the ground, changing the momentum, because this is not going to change. This moves with a constant velocity. Okay, the momentum Px will be Mvx. Am I right? There's no change in the momentum. It moves. Only this is the one thing which is going to give an opposite component. Okay, so of course this is this is a resultant vector. So when it hits, what happened? So this Vy component will give an opposite reaction, and then there is already Vx component. So that's along this direction. So the resultant vector will be this. So you get the ball moves like that. Okay, but your reaction is still on the same direction, same line. Okay, so that's what. So that's important. So it defines action and reaction as a pair of equal and opposite forces. Okay, the equal and opposite force, the reaction also should be the same magnitude force. Only direction will be exactly opposite. Okay, and forces acting along the same line. And this is very important. Action and reaction forces are always on the different objects. Remember that. If it is the same object, then of course it's the equilibrium. Okay, that means they cancel each other. Okay, if I give a ball one force upward and one force downwards, of course, then it becomes a balance, because I given an equal magnitude opposite. So it will not move at all. But here it is not. Equal and opposite forces happened because the forces were on different objects, not on the same objects. Okay, same object. Okay, this one. Then they give the consequences. Okay, the point is action force exerted by a body X on a okay, what they said is, so for example, if there are two bodies, let me call this as let us call this as X. This is one body, X, and this is another body, Y. Okay, so we are going to drop the ball. Okay, so the X is going to impart a force on Y. So, and similarly, Y will impart a force on X, which is the opposite direction, right? So, let the force imparted on Y by X, we call it as, what is the symbol they are using? The force exerted by a body X on a body Y, conventionally written as F of Yx. That means the X is imparted a force on Y, and the force amount is F. Okay, as a result, the body Y exerts a reactive force, correct? And that is a Y is going to apply a force on X, correct? So that is going to be what? F of XY, because Y is going to impart a force on it. Both the magnitude will be same. Yx will be equal to xy. Direction will be opposite. You got it now? There's no there's no question of cancellation. Yes, of course, because they both are different objects. Because this is exerting on this and this is exerting on this. So they won't cancel each other and all. This is an important thing. So this force, it is not that you have to hit. This is a contact. There's no need to be a contact force. Without contact also it can happen. Simple as a magnet. Okay, you have a magnet of one pole. Okay, you take opposite pole, you drop the magnet. Tuck, it bounces back. Okay, there. Yeah. Okay, so that's what. There also, you try to exert a force, there is no contact at all. Okay, and the other thing is your Earth, the force, gravitational force acting on the moon and the Earth and all, they are not in contact. They also have a reaction. Okay, every force acting, they will have an opposite reaction. Okay, so this is what your Newton's third law is. Okay, so I will stop here, and then in the next class, we will see about the inertial and the non-inertial frames. Okay, there are some problems, you should do it. Okay.